Okay, I'm back and I have added to my list of equations the volume flow rate. So volume flow rate is equal to the volume of fluid that is passing in a pipe per unit time. And then we also found out that it was equal to the speed of the fluid multiplied by the area of the pipe. And then also we had conservation of volume flow rate. So this is going to be true if there is no additional sources of pressure going into the pipe and then none of the pressure is leaving. So therefore the volume flow rate going in has to equal the volume flow rate going out. And then this is going to relate the speed of the fluid going in to the speed of the fluid coming out. Now we want to turn our attention to dynamic pressure. So far we've only talked about static pressure. And static pressure up here depended on your height. So now we want to talk about dynamic pressure, which is going to depend on your speed. And so when we, in our previous lessons, when we talked about energy, a second kind of mechanical energy was called kinetic energy. And it was 1/2 mv squared. Now this is useful when you're talking about solids, but when you're talking about fluids, instead of using mass, we tend to use density. So therefore that equation, 6.2, can be turned into equation 11.7, which is going to say that the pressure that you start with plus the additional pressure caused by the moving of the fluid has to equal the pressure that you end with plus the additional pressure caused by the moving of the fluid. So again, you got in, and then on the other side you've got the out for it. So here's a sample question. A fluid enters a pipe of cross-sectional area A with the speed V1 and a pressure P initial. It then exits the pipe with the same area. So the area that it went into the pipe over here is the same as the area it leaves over here. So we're going to say that this is A and then this is A over here, and they're exactly the same. Okay, so what is the new pressure that it's going to have? Well, first we need to know the speed. So if the speed going in times the area going in is equal to speed out and the area out, but the areas are the same, then that means we could cancel the areas, and then that would be telling us that the speed going in has to equal the speed coming out. Okay, then we're going to take those speeds and then plug it into equation 11.7. And since the speeds are the same, then that means that that term 1/2 rho v squared is the same on both sides of the equal sign. And so we can cancel it out. So now that means that the pressure going in has to equal the pressure coming out on the other side. So this says that if the area of the pipe doesn't change, then the speed of the fluid doesn't change. Okay, but this time, let's assume that the fluid in the previous question exits a pipe that has 1/2 the original area. So this time, we're going to have a situation where the pipe is going to get smaller. So it's going to do something like this. So now the area is going to be 1/2 of what it was before. So it's going to be 1/2 of the original area over here. Okay, so now if we take 1/2 the area, then that must mean that this has to get bigger in order to compensate. So if this gets smaller, this gets bigger, and it gets bigger by a factor of 2. So therefore, if the speed going in is v, then the speed coming out is 2v. Okay, now that we've got those speeds, we can plug it into equation 11.7. Now remember, you have to square the speed, so that 2 squared is going to be 4. Okay, now we're going to rearrange it for p sub 2, and then it turns out that p sub 2 is equal to p sub 1 minus 3/2 rho v squared. So notice it's going to be smaller because you subtracted that piece that was the dynamic pressure. So the pressure is then going to decrease as it goes through the pipe. Okay, another way of looking at this is airplane wings. So a airplane wing is not going to be shaped like this, where it's has the same shape on the top and then on the bottom. So notice that the airplane wing is deliberately changed so that it has a flat surface on the bottom, and then it makes a kind of a shape like this on the top. So that means that the air, okay, so let's say the wind is going in this direction. So some of it is going to have to go the long way. So some of that air has to go this way, and then some of that air has to go this way. And so notice that this has a shorter route that it has to travel, and this has a longer route. But it has to do it in the same amount of time. So the time it takes for the air to go across the top of it has to equal the same amount of time it takes to go the short way. So if speed v is equal to distance divided by time, and if this is larger because it had to go a longer distance, r is going to be larger, so it's going the speed of the air has to be going faster over the top than it is going down the bottom. So again, we could say that the velocity on the top, put a big V for on the top here, and then put a little v for down here on the bottom. Now what difference is that going to make? So now we're going to use our equation for dynamic pressure. So the pressure going over the top plus 1/2 rho the velocity going over the top has to equal the pressure on the bottom plus 1/2 rho v the velocity going on over the bottom squared. But notice that if this thing is larger going over the top, so then that means that the pressure has to be smaller. So in order to understand this, think about 1 plus 7 is the same thing as 7 plus 1. So 1 plus 7 is 8, and then 7 plus 1 is 8. So notice that if this number gets small, this number has to get big in order to compensate. And that's the same situation that we have here. If you go over the top, the velocity is larger, so therefore the 1/2 rho v squared over the top is larger. So in order to compensate, the pressure gets smaller. And then since the velocity over here is smaller, the pressure gets larger in order to compensate. So that means the pressure is, this would be the pressure on the bottom, is pushing up on the airplane wing. And it's going to be greater than the pressure that's pushing down. And so this is what's going to give an airplane wing lift. Now what about if the airplane decides to turn upside down? What do you think is going to happen? Well, it's not going to get any lift, because now the airplane wing has been inverted, and so now there's going to be a pressure pushing down on the airplane wing that's going to be stronger than the pressure pushing up. And so that airplane's going to go into a dive when it flies upside down. Okay, let's take a break, and when we come back, we will then talk about what is the total pressure on a fluid.